Hi, grade 10s. Welcome back to getting prepared for the exams, for the June exams with the learning space. So today we're going to be diving into waves, sound, and light. We're also going to be doing electrostatics and electric circuits. So this is going to give you a very good understanding of whether or not you're ready for your exams. If you struggle in this session, it means maybe you need to go through a little bit more in your preparation. But yeah, so whether you're joining us on Zoom or on TikTok, get ready to learn, engage, ask questions. There is a chat, so if you need to ask any questions, then you're welcome to do so. This is all about helping you gain your confidence and to sharpen your problem-solving skills for your exams. Don't forget to subscribe and like our content on YouTube. And this will really help us grow our community so that we can continue offering free tutoring sessions to students all over South Africa. So let's get started. So we're starting off with just a summary of all the concepts that we're going to be going through in the past paper. So we're going to start with waves, sound, and light, go through a little bit of the basics there. I'm just going to do a very quick run through, look at the equations, what you need to know for your test. And then we're going to do electrostatics, and that looks at charges and what happens when you bring two charges together, what happens when they separate, what is the transfer of electrons there. And then finally, my personal favorite is electric circuits. And yeah, then we'll just go from there into a past paper and then we'll see how it goes. Okay, so first off is sound and light and waves, right? Now this is a fairly simple section. If you remember how to apply all the formulas and you remember what all your definitions are, you really shouldn't struggle that much. So first of all, when we look at waves, we first start off with what is known as a pulse. Now, a pulse is a single disturbance in a medium, right? And so when we have, let's say, there's a man and he is holding a rope at the gym, and he's holding a rope. You know, the people at the gym that like wave ropes around and causes this rope to move up and down. He's creating a wave. But the simplified version of that, when he first does his initial first lift up of the rope, that's called a pulse. So when we have one single pulse, that's called a pulse. And then when we have lots of them going up and down and up and down, that's called a wave. So now waves can be separated into mechanical waves and electromagnetic waves. So mechanical waves are the ones that need a medium to go through. So a medium is like air or water. It needs something to be able to go through so that it can be transmitted. It's basically a sharing of energy between particles, right? So if you're looking at your rope analogy again, you have a bunch of particles lined up in your rope, right? And so when you first excite this first one and push it up, it transfers the energy that it's getting from that initial push to the next one. And then the next one gets energy, and then the next one gets energy, and then they all increase, they all move up and down because of that first initial impulse. And so that will have them move up and down because they're transferring energy between each other. Now, in our mechanical waves, we have transverse waves, right? And these ones are, we have a definition here that says particles of a medium that vibrate at right angles to the direction of motion of waves. So we'll look at this in a little bit more detail just now. But yeah, just know that this one, we are moving, the particles move at right angles to the direction of the wave, whereas longitudinal waves, they vibrate parallel to the direction of the motion. And then what distinguishes mechanical waves from electromagnetic waves is that electromagnetic waves do not need any medium to go through. So they can go through, they can transfer this energy without any medium in between them. So the first we said is a transverse wave, right? And so this looks like a wave we've seen before. This one feels a lot more familiar than the other two. And this is basically when you have a wave and if you look at, if you were to observe a particle on this wave, like over there, you would actually see that although the wave starts over here, the wave starts here, right? And it's somebody pushing this end of the rope up and down, right? And it looks like, so it'll first start off as this part will move up and down, right? And then it'll transfer, and the rest of the wave will continue to move. It will look like the wave is moving that way. So like these waves will kind of like move from left to right. It'll look like this wave is being carried through the rope. But what you'll actually see is that when you look at the individual parts of the wave, is that you'll see that these particles actually don't move from left to right. They're just moving up and down. Sorry. They're just moving up and down. And so this is the case for every single one of these particles on this wave. None of these are going to be moving from left to right. Every single one of them is just moving up and down. And you can actually look up, there's lots and lots of YouTube videos that you can look up on this, and it'll show you how, even though it looks like this wave is going to be moving towards the left and to the right, it's actually just moving up and down, right? All of these particles are just moving up and down. And so the first thing we see when we look at this wave is that there's these peaks and these divots, so like not divots, but like, what is this? Valley. So if you were looking at a mountain range, or you're looking at a group of mountains, you would see, I was just trying to erase these, you would see that let's say there's a little man. I think I'm going to abuse this little man by the end of this. He walks up this mountain and he gets to the very top. There you go, right? And he's at the top of this mountain. He's saying, I'm on top of the world, right? And what we say when we're referring to a wave, this point that he's at the very top of the wave, is called a crest, or this bump that goes up over the rest position. We'll talk about the rest position, is called a crest, right? And then when he walks down, 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 it gets to the bottom of the mountain. We say that he's in the trough, so like the bottom half of the wave, right? And so those are the first two things that we look at. We look at the crest and the trough of a wave. So the up part of the wave is the crest, and the bottom part of the wave is called the trough, right? Now, this position where the wave starts, let's say, again, this is a rope. When it's first laying flat or in its rest position before any waves have been introduced to it, we call this the equilibrium or the rest position, right? So it's either called the equilibrium position or the rest position. And this is where all of your points start off at the very initial, before your wave starts to propagate, all the particles start on this rest position. And it's from this rest position where we get our amplitude. Now, our amplitude is basically the distance between the midpoint, or the distance from the middle of or the rest position. So in this case, it's labeled A, to the top of the crest, right there. Okay, and so that is what we would look at as our amplitude. Now, sometimes they try to trick you, and they'll give you a wave that looks like that, and they'll tell you, okay, there's my wave, and they'll tell you that the distance between this and this is 6 centimeters. Ooh. Oh, I can use this. Let's do this. They'll tell you this is 6 centimeters, and then they'll say, what's the amplitude? Now, we know that the amplitude, like we've just said, is the distance from the midpoint here to the top of the crest, right? And so that means that our amplitude isn't going to be 6 centimeters, but rather half of 6 centimeters, which is going to be 3 centimeters. So our amplitude is actually 3 centimeters. Okay, and so that would be our amplitude. Now, you'll see that in a wave, we get these points, like we said, all the points move up and down. That's all we're going to experience in our wave. We just have points moving up and points moving down, right? Nothing is moving from left to right. Now, you get points that are actually very similar in the way that they move, right? So let's say I have this point of, let's say this point over here and this point over here. If we look at, let's say this is point 1 and this is point 2. If we look at point 1, we see that at this point in time, so this is just a graph of just how the wave looks, right? Nothing too fancy. If we look at position number 1, we can see that our wave was going up and then it's now going down. We can see that the gradient is down, so it's moving down from its up position where it was at the top there, right? And then the wave continues and it goes down and then goes back up again and then comes down. So we can see that point 1 and point 2 are essentially going through the same motions. They're at the same position at the same time, and they're both going down at the same time. And so we call these 2 points, we say that they're in phase, which means that they're going in the same direction at the same time, and they are in line with each other essentially. And so points 1 and 2 are in phase. Let's look, what other points could we have that are in phase? We could also have 2 points here at the crests. So at the top of the crests, point C and G, those 2 points are both at the top of this hill and are about to start coming down this hill over here. And so we can say that those 2 are also in phase. But one of the tricky ones that you can see is B and D. Can you see B and D are along the same position in the rest position, but B is currently on its way up. Like it is going up, it's not going to go left to right, but it's on its way up this wave, whereas D is actually coming down. It's just come up from its up, it's coming down. And so those 2 aren't in phase. Those 2 are going to be out of phase. So we can't say those 2 are in phase. Don't get confused by that. Okay, so that's a transverse pulse or transverse wave, transverse wave. If it was just one of these, it would be a pulse, but this is a transverse wave, so it's going to go up and down. Okay, cool. And then we get to the principle of superposition, right? And this deals with pulses. And it says the superposition is the addition of the amplitude of 2 pulses that occupy the same space at the same time. So here, what we'll see is that if a crest is considered positive and a trough is considered negative, right? And so here, I'm sure we are familiar with this, is that if you have 2 pulses, right? We have pulse A and pulse B. So we said pulse is just one single disturbance. And so it's just 2 single disturbances. So they're not connected yet. They're just 2 single disturbances. And we have pulse A moving towards the right and pulse B moving towards the left. Let's say they're part of the same rope over here. Pulse A has an amplitude of A, and pulse B has an amplitude of A as well, so they have the same amplitude. When these parts, so let's say this is, like we said, this is part of the same rope. When these 2 come together, right, we will see an addition of their amplitude. So this will create one bigger wave, right? And so when these 2 come together, they're going to collide and they're going to form a bigger wave. And the size of the amplitude for this wave is just going to be the amplitudes of the individual waves added together, right? So here, our amplitude here is going to be A plus A, which is going to be 2A. So if this amplitude was, let's say, 3, let's say this amplitude was 3 meters, right? So then that means that if we have 3 meters here and 3 meters here, then that means it's going to be 3 plus 3, which is going to be 6 meters. This is how long, how big, how tall it's going to be when they collide. And then after that, they will continue to move in the direction that they were moving in before, right? So we know that pulse A was moving to the right and pulse B was moving to the left, right? And so pulse B will continue moving to the left. You'll see that the wave will continue moving that way, and this one will continue moving that way. And so we have our 2 pulses. They came together, they were moving on their own respective paths on the same rope. They collided and caused the amplitudes to double, not double, but become added to each other, giving us a larger amplitude. And because they were both crests, we added them together. And so after that collision, they then move away from each other in the original direction of motion. Okay, now the same happens with a trough, except now in the way that we looked at a crest as a positive. So if you look at a crest, you'll get a positive value, right? Or you'll see a positive, you should see like a little positive in your mind. Whereas a trough, you're going to look at it as in negative, right? Because if we have, if we look at it in terms of displacement, we'll have the axis or the reference point here is 0. So anything above the reference point is going to be a positive, and anything below the reference point is going to be a negative, right? So then that means that we're going to add anything that's above the reference point and subtract anything that's below the reference point. Okay, and so here, if we see again the same thing, let's say this was, this amplitude was 5 meters, and this amplitude was 2 meters, right? So what we'll see is that they'll move along the rope. This one is moving towards the right, this one is moving towards the left. And then when they collide, they won't form as big of a bump as the first one because these ones are being, they're working destructively, right? So we call this destructive interference. The first one was constructive interference. So they won't form a big bump, but rather they'll form a bump that's the size of the two waves combined, right? So here it would be 5 or positive 5 minus 2, which will give us 3 meters. So it won't be as high as the 5-meter one, but it will be still above the reference point. And then again, like we said before, they will continue to move in their original directions after the collision has happened. So this one continues to move at 5 meters, and this one continues to move at, and will be 2 meters in terms of the amplitude. Okay, so that's the principle of superposition. This is a very simple question that you could get in the exam, so just make sure that you're feeling comfortable with this. Okay, does anybody have any questions? You're welcome to write any questions in the chat, and then I'll see them, and then if they pop up, I'll try and answer as they pop up. Okay, I don't see any questions, so I'm going to move on. So then we have our two first points of calculation. So we looked at wavelength, which is something that we may need to calculate, but we have our period and frequency. Now, our period has the symbol T. Now, I don't want you to get mixed up between T and what the actual unit for a period is. T is just what we write. Instead of writing period equals this, this, and this every single time, we have just, or some scientists have just decided that T is going to be what we use to refer to the period of a wave. And so the period is the time that it takes for one complete wave cycle to pass a fixed point. Now, we didn't actually look at a wave cycle, but a wave cycle is the point between two points that are in phase. So over there and over there, we said that points, this point over here, let's call it A, and point B are in phase. And so usually when you're asked for a period, or if you're looking at an amplitude time graph, the period is the time that it takes between 2 points of phase, or for one complete wave cycle to pass. So this over here, for the wave to go up, down, and then come up, start coming up again, that's one wave, right? The frequency is the number of wave cycles that pass a given point at a specific, in a specific amount of time. And this is measured in hertz, sorry. So period is measured in seconds, and frequency is measured in hertz. Now, there's a very nice relationship between period and frequency. So period is actually, they're inverses of each other, sorry. Period is equals to 1 over frequency, and frequency is equals to 1 over period. So if you're given one, you have the other one. So you can't make the excuse of, oh no, we weren't given frequency and I needed to use frequency in my equation, because they're reciprocals of each other. If you get the frequency, that means you automatically get, not automatically, but you can find the period, right? And so high frequency means that there's a lot of the same wave repeating over a short period of time. And low frequency mean that you'll get like 1 every 2 seconds, or like 1 every 5 seconds, one crest or one wave passing by a point every certain amount of time. So if you have a lot of waves in a short amount of time, then we can say that that's a high frequency. If you have a very few waves in that same amount of time, we say that it has a low frequency. Now, the equation of, or like the biggest, not the biggest, but the nicest equation. I like triangle equations because they always make sense. So here is where we calculate the wave speed. Now it's measured in meters per second. And be careful when you're writing this meters per second. You can either write it in meters per second, which means that it's meters over seconds, right? Or you can write it as meters second, but you have to put that -1 there. You can't just say meters dot seconds and then leave it like that, because that means that you're multiplying meters and seconds, or you're multiplying distance and time, which is not what speed represents, right? So the way that I learned it when I was learning the triangle method of using of any distance over time and any triangle based equation, is that if I want to find, let's say, the speed, I have to cover it up. So I cover it up with my finger. So let's say I'm looking for speed. I cover it up with my finger, and then I see what do I have left in my equation. So let's say I'm looking for speed, right? I'm just moving up so that I can show what, okay, maybe let me draw a shape here so that it's not as confusing. So let's see. Is it going to draw me a full shape? No, it's not. But yes, let's just pretend that this wave speed is covered. That means that I have frequency and wavelength left, right? And what I do with that frequency and wavelength is I multiply them. So whenever it is right next, if they're two, if it's frequency and wavelength next to each other, I'm going to multiply these two together. And then if I'm looking for, let's say I'm looking for wavelength, I cover up wavelength, I'll erase it just now. And now I have wave speed over my frequency. And that means that I'm going to say wave speed divided by, so here it would be a divided by my frequency to get my wavelength. So if I wanted to find the equation of my wavelength, I would say, so let's say if I had wave speed and I had frequency and I'm looking for wavelength, I would say wavelength is equals to wave speed, which is V over frequency. Okay, cool. And now this is not one that, oh, sorry, this is the wrong symbol. Wavelength is that one, sorry, I drew angular velocity, but that's how you would find your wavelength, right? And now what happens if I give you the period instead of the frequency? Well, you know how to do that, right? If I give you the period, then you're just going to say here, 1 over the period is equals to the frequency. So whatever you get for that 1 over the period, you're going to substitute in there. Okay, then we have longitudinal waves. I'm going to go through these ones a little bit quicker because basically the same things that we have, except longitudinal waves. So I'd like to imagine the only nice, really nice way that I see this coming is, see this in real life, is when you have like those slinkies, those like springy toys. They're not really springs because they don't bounce back, but there's those coils, right? And you can play with them and you can push them and you can make them go down the stairs by themselves. Now that's what that's a very good representation of a longitudinal wave, right? And how we can tell that something is a longitudinal wave. So sometimes they'll give you a longitudinal wave and they'll say, how do you know this is a longitudinal wave, right? Now, remember with our transverse waves, we saw that we have our wave and it goes up and down and up and down. And we say all of these particles move. Ooh. We said all of the particles move. Oh my gosh. Maybe if I draw it slowly, there we go. All of the particles just move up and down about this rest position, right? While the wave moves from the left to the right. The opposite, not the opposite, but something is different when it comes to longitudinal waves. What you'll actually see is that the wave moves from left to right, but your particles also move from left to right. And what you get is that, so let's say somebody has their hand over here. I'm going to try and draw a hand. somebody has their hand over here and they're pushing this the spring forwards and backwards and forwards and backwards and forwards and backwards. What you'll get is you'll get these parts of the wave that are clumped up together, and those parts we call the compression, and the parts that are further away from each other we call them rarefaction, right? So not refraction, not refraction, it's rarefaction, right? And then our amplitude works in kind of a similar way. How we had our amplitude before be this between this rest position and the top of the crest. What you'll see is that because your particles move from left to right, there's an equilibrium position before they get to so like you'll get a very, very tightly compressed section, right? And your particle will be moving from there to there. They'll just be moving left to right. And this will be your amplitude. But they rarely give the longitudinal one, but just so you know what the amplitude looks like, because your particle is just moving from left to right. This is the amplitude that your particle will have. Wavelength, again, is the distance between two waves. So here we're looking at our wavelength as being between the middle of a compression, or the middle of a refraction and then the other middle of a refraction, or the middle of a compression and the middle of a compression. So there and there would be your wavelength. Okay, so we looked at compression, refraction, amplitude, wavelength. Frequency, again, is how many waves, complete cycles, move past a point in a certain amount of time. And period is how long it takes for one full complete wavelength to go past. And then wavelength is still the same. V is equals to frequency times our wavelength. It's still the same as with our other wave. Okay, then we get to the funky one. Now this one has a lot of theory behind it, so we're not going to go through the theory because that's just memorization. But we have electromagnetic waves, and these are made from electric field and magnetic field. So you guys don't really need to know the nitty-gritties of it, but what you need to know is how they look. So basically, you'll have a wave that's going in, let's call this the Y direction. No, this is the X direction, and then Y direction. But they just oscillate between those two planes. So you'll get a wave in one plane, so you'll get this wave in maybe let's say the XY plane, and then you'll get another wave in another plane, which is that one, right? Now, what's special about these, like we said at the beginning, these don't need a medium to move through, and so they can move without a medium. Okay, electromagnetic radiation, this is where you get your different wave lengths and you get your electromagnetic spectrum. Now, one of the key things that you need to know is that wavelength is inversely proportional to frequency, right? And so if we have a long wavelength, so let's say radio waves have very long wavelengths, you guys probably have learned about some kind of mnemonic to remember the way that the electromagnetic spectrum is laid out. But I have this one over here. A good xylophones use very interesting musical rhythms. And this one is going from the shortest wavelength to the highest wavelength, or the longest wavelength. And good stands for gamma rays, xylophone stands for X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves, right? So like I was saying, wavelength is inversely proportional to frequency, which means that if you have a low frequency, that means you have a long wavelength. And if you have a high frequency, that means you have a short wavelength. Okay, now another mnemonic that you guys would need to know, or I'm not sure if you know it as a mnemonic or just remember the colors of the rainbow, but this is a very nice question that I like to ask quite often, is which color has the longest wavelength? Now, so we start from red, orange, yellow, green, blue, indigo, violet, all right? So the colors of the rainbow. And so that would, your red has got the longest wavelength, and so it has the lowest frequency. So that's just something that you need to remember for your test. Okay, now finally, we get to the electromagnetic radiation calculation. So this is the same as we had before, right? So this is the same as V is equals to frequency times wavelength, except here they've changed our V into C. So it's basically the same formula, but we have our V as C. And the C is the speed of light, right? This is the speed of light, the speed at which light travels in a vacuum. Now, this is always a constant. It's always given as this. And so whenever you're getting asked electromagnetic questions, you know to use your C as this 3 times 10 to the power of 8 meters per second. Okay. And then we get the nature of a particle. So this is where, okay, so electromagnetic radiation isn't continuous. So like where we had with a rope, right? It was continuous, like one particle touched another particle, which transferred energy in that way. But it's actually made of like these tiny little energy packets, right? And these energy packets are like, let's say I have a beam of light. Let's say I have a torch, right? Like the ones that you have at camp, or yeah. What you see there is just like tiny little, they call them energy packets, right? And they're moving with each other and they're transferring energy to each other. And what we call these tiny little packets, we call them photons, right? And we called it, the definition for it is the smallest indivisible quantity or packet of energy that light and other EM radiation consists of. Okay, so this is a definition that they ask quite a lot and that you need to know. So yeah, so this is just what photons are. So whenever you see like photon, you might be wondering, what are they talking about? They're just like tiny little packets of energy, and they're usually seen in light. Okay, now the last formula that we need to know for waves is this equation for the energy of a photon. So we looked at the photon as a little packet of light. And so usually they'll ask you, what is the energy of the photon? And the way that we calculated this equation is also on your formula sheet, is E, which is the energy of the photon, is equal to H, which is Planck's constant, which will always be this value. So 6,63 times 10 to the minus 34 multiplied by the frequency. Now the frequency, we've seen it before in our transverse and longitudinal waves. So we know, we're familiar with what a frequency is. And so, yeah, this is the equation that we'll have. But we'll look at it with the equation next to our past paper when we try it. Now, I'm going to speed through electrostatics because this one is not that difficult. So we know that atoms are made, atoms have positive and negative, they have positive protons and negative electrons, right? Our positive protons are in the nucleus and the electrons are floating around the atom, right? They're on the outside of the electron. Now, when we have a stable, or like not a stable atom, but when we have a neutral atom, the number of electrons is equal to the number of protons. We know this, right? From chemistry, we know that a neutral atom is one where the electrons is equals to the protons. And this is called a neutrally charged atom, right? Now, when we have a imbalance between our negative, positive electrons, that's where we have either positively charged or negatively charged electrons. So positively charged is when we have more protons than electrons, and that makes sense. If we have more positive barbs, no, that was terrible. If we have more positive protons, that means we're going to be more positive. So we're going to have a positive charge. So we say we have a net positive charge, or we have a deficit of electrons, right? If we have too many electrons, means that we have too many negatively charged particles. So that means that we'll have a negative charge and will be in excess of electrons, right? So neutral means that we have the same number of electrons and protons. Positively means that we have less electrons than protons. And negatively means we have more electrons than we have protons. Okay. And so this one is simple. I think we've been doing it since grade 7, how like charges repel each other. So if we have two positively charged particles coming close to each other, they'll repel from each other. So they'll try and move away from each other. Whereas unlike charges, so a positive and a negative, will have an attraction between them. And this is the electrostatic force of attraction that pulls them together. Now, we have two primary definitions, right? The first one is the principle of the conservation of charge. And this is that the net charge of an isolated system remains constant during any physical process, right? And so this is when we have two particles and we bring them together and they touch, and then they usually ask you, what is the charge after they are separated? So that we use the principle of conservation of charge. And then the second one says that every charge in the universe consists of an integer multiple of electronic charge. This one is not as common, but it still needs to be known. It just means that we need an integer number of electronic charge. So we can only have +1, +2, +3. We can't have +1,5 charge. We can't have that. So it always has to be an integer, right? And so these are the two formulas that we are given. This one we use in the case where we are asked, what is the number of electrons? So let's say they give you a particle, positive, negative. They come together and they touch and they exchange electrons. Quiz, in which direction do the electrons move? So we said this one has excess electrons. So let's say it has 3 excess electrons. This one is, let's say it's just 4 excess electrons. This one is missing 2 electrons. So the electrons will move from the negative charge to the positive charge. Okay, so that's how the electrons will move. Then they'll say, when they separate, how many electrons were transferred, right? Now this Q, this will come with a charge. So it will have like 5 coulombs. And this will have like, this is a positive 5 coulombs, negative 10 coulombs, just as an estimate, right? Then they put together and then they separated, right? In our equation, using this equation, this is the one that we use to determine what the charge is at the end. So we'd say 5 plus minus 10 over 2. So it's 5 minus 10 over 2, which will give us minus 5 over 2. So it's negative 2,5 coulombs for both of them, right? Now, they'll ask how many electrons were transferred. This over here is the change of electrons, or what electrons moved from one atom to another. So we'll do an example. There's one in the past paper, but just make sure that you know that this is not the new charge that you have on your atom, but rather the change in electrons from one, or how many electrons were transferred from one atom to another. Okay, and then this is just conversions. So the main ones are the picocoulombs, nanocoulombs, microcoulombs, millicoulombs. We know that our charge is calculated or presented in coulombs. And so we always have to do our calculations using coulombs. And so to get from picocoulombs, we times 10 to the 12, nanocoulombs times 10 to the minus 9, microcoulombs times 10 to the 6, and 10 and millicoulombs is times 10 to the minus 3. So I used to always remember it as num. I don't know if that helps, but that's how I remembered it as MUNP. So it goes in that direction. Okay, we have the charge of an electron, which is our Q. Sorry, here Q is our charge, is our number of electrons. Sorry. Yes, and then the charge of the electron is that. Okay, and so now finally the electric circuits, my favorite. Okay, this one we're gonna really speed through because we've been doing it for a while now. We first start off with potential difference, and we know that that's just a form, that's just a definition we need to know. So work done per unit positive charge. and we know that our voltage is equal to our work, which is in joules, and our charge, which is in coulombs, right? Our current is measured in amps or A. The current has symbol I, and it's the rate of flow of charge. So Q is our charge, again measured in coulombs, and T is in seconds, right? And then we know the resistance is R, and it's measured in ohms, and this is the material's opposition to the flow of electric current. Then we look at Ohm's law. This one isn't given to you on your formula sheet, but if you've done enough practice, you don't need it on your formula sheet. We know this is voltage, and we looked at the definition before. We know this is current, and we know this is resistance. Now, from this, we can see that as we increase the voltage, we are going to increase our current. So our voltage, current, and the same for resistance. Yeah, okay, cool. Now, let's see. Okay, then we look at series and parallel circuits, and calculate the resistance, current, and voltage for those. So we know that a series is a circuit where there is no current branching. There's no other path for our current to flow. So our current is going to move from the positive, it's going to move around, go through the light bulb and go around there. So there's no place for the current to branch out and try and do anything else. It follows just one path. So this is how we tell when something is series versus a parallel, which we'll look at now. But if we have multiple different resistors in our circuit, then to calculate the total resistance, we just add them up. Our current throughout the circuit is going to be the same, so there's no division of our current. So our current here is going to be the same as our current here, is going to be the same as our current here. And the voltage, if we have more than one resistor, we add those up. So voltage of 1 plus voltage of 2 will equal the total voltage, which is the voltage that our battery is going to provide. All right. Now, for parallel, there is a chance for our current to divide, right? So we have, let's say we have our battery there, and we have our first resistor there, and we have our second resistor there, right? Now, before we said our current didn't have anywhere to go, like it just had that one path that it went down before in our series. But here, our current's going to move up there, then it's going to move. I'm trying to make this a little bit thicker so that you can see it. Oh, there we go. There we go. So our current's going to move. Our current's going to move there. And then when it gets to this junction over here, it's going to have to decide whether it wants to go to the right or it wants to go down. And so that's how we can tell where our parallel, that we have a parallel circuit, is that our current has the opportunity to divide and branch off into two separate parts. And then it actually loops around and then rejoins over here and comes back to this cell, right? And so our current starts off as our current total there, right? And then it splits out if it to current 1 and current 2 there. And then it regroups again here to give us our current total. And then, yeah, so that's kind of how our current is divided. The voltage is the same for all parts of our parallel branch. So the voltage here is going to be the same as the voltage here. It's going to be the same as the voltage here. And then our resistance, finally, this is a little bit of a tricky one. If you had 3 ohms here and you had 5 ohms here, then to find the total resistance, you'd have to say 1 over, so RP is the total resistance. So you'd say 1 over 3 plus 1 over 5, and then you'd solve this, making sure that your final answer is not in the form of 1 over RP, but in the form of RP. But we'll do a question like that and practice that a little bit. And then This one is just a quiz to see who is paying attention, which one is the series circuit and which one is the parallel circuit here. Yeah, you guys can put it in the chat. I'll give you 30 seconds. Which one is the parallel circuit and which one is the series circuit? Perfect. Okay, cool. Thank you, Jessica. The circuit B is the series circuit, and then circuit A is the parallel one. We see it here where we have our current flowing down here. So our voltage doesn't really take any resistance, so we don't really count it as drawing any resistance. So our current just continues to go. So we'll have our current be the same everywhere. And then in our other circuit here, it reaches this junction. It could either go this way or this way. So that's a branching of a circuit right there. And then it'll come rejoin again there. There we go. Okay, now we finally get to our past paper. Okay, let's see what we have. Okay. Okay, so we have our first question, and it says the distance between 13 consecutive wave crests in a ripple tank is 1.8 meters, right? And the waves travel through the water at a speed of 0.25 meters per second. So here we're dealing with waves, right? So this is the second question. So there's multiple choice questions, and then we come to this question, and it is dealing with waves. So now when we try and visualize it, we can visualize it like this. So we'll start at, they said how many? 13. So I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right. Oh, it's gone. It looks like a control swirl on here. But anyway, if I have 1, 2, 3 up until 13, right? They've told us that the distance between 13 consecutive wave crests, right? So we don't know if this wave starts at the bottom here and then gets to a crest, or if it starts at a crest and then ends at a crest. Like, we don't know where it starts necessarily, but we know that the distance between this and this over here, that's one wave, right? Then we have another wave here, right? Then we have another wave going all the way to 13. So if you count these, you'll actually count 1, 2, 3. You'll count 12 crests or 12 waves with those 13 crests. Can you see here we have 1, 2, 3, 4 wave crests, but we only have 3 waves within those wave crests. So the first question is, what is the wavelength of a wave? And so we know this is just a definition. We would say that this is the distance between 2 consecutive or successive points that are in phase. So I'm not going to write that out because we know that that's just a definition that we need to remember. But the second question says, calculate the wavelength of the wave in meters, right? And so we know that the equation for our waves, okay, let's see if I can put, there we go. Let me put this up there, or maybe drag it up there. Let's drag it up there. We know that these are the formula that we're given for waves, and we don't see any formulas here but we can see a few formulas. So we have this formula here that says V is equals to, or the speed is equals to the frequency times the wavelength. And we have the speed, so you could say, oh, okay, let me just use that one. but we don't have the frequency, and we don't have a period. We don't have anything actually. We just have our speed, but we don't have the wavelength. We just know that there's 13 wave crests, and we want to find out, and they take 1.8 meters to complete. So the first question is actually going to help us answer the second question. So if we can get that, then we'll know that we're secured for the second question. Sorry, I'm just trying to get my razor to work, but it's misbehaving a little bit. There we go. Okay, so we said when we look at this diagram over here, between 1, 2, 3, 4 wave crests, we have 1, 2, 3 waves, 3 complete waves, which means that we have to, how many waves are we going to have in that 1.8 meters? What do you guys think? We're not going to have 13 waves because in this four crests, we only have 3 waves. So that means we're going to have 12 waves. And if it tells me that I have 18 meters and it takes 12, or that in those 12 waves are taken by 1.8 meters, that means to find the wavelength of one wave, I have to say, so the wavelength is going to be equal to 1.8 over 12, right? So this is the total length of the wave, and to find the length of one wave, I'd say 1.8 divided by 12, and this should give me 0.15 meters. So that's the length of one wave. Okay. Then they say, what is the frequency of the wave? So now we have the wavelength, we have the speed. So what do you guys think? What is the frequency of the wave going to be? I'm going to give you 1 minute. It shouldn't be that difficult. And remember, our frequency is in hertz. It hurts so bad. No. Okay, so we're doing 2.2. We're trying to find the frequency of the wave, 2.2.2. We're trying to find the frequency of the wave. We've done 2.2.1. And so the frequency of our wave, we're actually going to find a 2.2.2. We're going to use the formula that we're given in our formula sheet that says speed is equals to frequency times wavelength, right? Or we can use our triangle. Remember, our triangle says that we'll have our speed here, we'll have our frequency here, and we'll have our wavelength. So if we're looking for our wavelength, we cross it out and we'll say, okay, that means that it's speed over frequency. So here, let's just rearrange this. We know that our wavelength is going to be our speed over our frequency. We know that our speed we were given as, what were we given our speed? 0.225 over our frequency. Oh, what are we looking for? Oh, we're looking for the frequency. Sorry, we're looking for the frequency. We have the wavelength. So we have the wavelength. We're looking for the frequency. So our frequency is going to be, oh, sorry, that is terrible. So we're just going to swap these around. These to be erased. So we know we're looking for our frequency is equals to the speed over our wavelength, and we said our wavelength was 0.15. So that means that our frequency is going to be 1.5 hertz. Sorry about that confusion, but there we go. Okay, now let's see what the next question says. Okay, so they love giving graphs. So this is a transverse wave because we can see that it's moving up and down. And it says, the graph shows the displacement of a leaf on a dam at intervals of 0.25 seconds after a disturbance has moved through the water and the wave is moving at 12 meters per second, right? So here this graph is showing what they're saying is that we have a leaf. I'm going to attempt to draw a leaf. We have a leaf that's on a dam, right? And it's moving up and down. There's like a wave that has come on the dam. Somebody's dropped a pebble in the dam or something. And so now this leaf is going up and down with the wave that has been formed on the dam. And they take the displacement every, they tell us what the displacement is every 0.2 seconds. So there we go, 0.2, 0.4, 0.6, 0.8, right? Now, they say at position C, is the leaf moving upwards or downwards? What do you guys think? Is it moving upwards or downwards? At position C, which is right here, is the leaf going to be going up, continue going up, or is it going to be going down? This one shouldn't be too hard. Is our leaf going to be going upwards or downwards? Perfect. It's going to be going up because it's already on the trajectory to be going up. So that's perfect. Okay, our leaf is going to be moving upwards. I'm just going to put it. So for okay, perfect. So for 2.3.1 is going to be moving upwards. Okay, now 2.3.2, it says consider points A, B, C, and D in the diagram. Identify 2 points that are in phase. So I want A and B, A and C, C and D, A and D. Which ones are in phase with each other? What do you guys think? Okay, I'm seeing an A and D. A and D. That's perfect. Okay, cool. So we can see that they're both at the top of the crests of their respective waves. And so that's a more than enough sign to tell us that they are in phase. Perfect. So A and D. Perfect. Okay. Then the next question says, calculate the frequency of the wave. Now, we know that, what are we given? Okay, we're given at intervals of 0.2. So we know that over here, our time is 0.2. Over here, our time is 0.4 seconds. So this is a time versus displacement graph, right? So we are looking for, what is the frequency? We said the frequency is the number of pulses that pass a wave in a specific amount of time. Okay, so here we know that after 0.8 seconds, how many pulses have passed this point? Or how many waves do we have after 0.8 seconds? We have, let's see, we have one, we have one wave, then we have 2 waves, right? And so we can say that to find our frequency, so 2.4.1, 2.4.1, we can see that our frequency is the number of pulses that number of pulses over a specific amount of time. So that's what gives us the unit of hertz. And so to find our frequency, we say, okay, there's 2 pulses in a span of 0.8 seconds. Oh, 0.8 seconds, sorry, it should be down here. And so our frequency is then 2,5 hertz. Okay, so now that we have the frequency, what is our wavelength? I'll give you guys 1 minute, 1.5 maybe, wavelength of this wave, or 1 pulse. Keep in mind we were given the speed, so we could use that, and we know that on our formula sheet we will have a formula that uses the speed, the frequency, and the wavelength, so we can use that to find our frequency, our wavelength, sorry. So what is our wavelength? So we're trying to find the wavelength of this wave. We found the frequency, and so we are trying to find the wavelength. Okay, I see an answer. Okay, cool. So we know that if we use our formula, V is equals to frequency times our wavelength. Our V is our speed. So they've told us that our speed is 12 meters per second. So we can say 12 is equals to the frequency, which we've calculated as 2,5, and we're going to multiply that by our wavelength, or we divide both sides by 2,5, and so we can get our wavelength as 4,8 meters. Perfect. Okay, cool. Then they say what is meant by the term amplitude of a wave, and we know that the amplitude is just the distance from the rest position here to the top there. So in our case, they said this displacement is in centimeters. Ooh, sorry, centimeters. Yeah, so never mind. Centimeters, and so our amplitude here would be 10 centimeters. So that's how high from the rest position this droplet of water has moved. And then they ask a question, the amplitude of a wave is now doubled. So they've doubled the amplitude. What is the value in meters of the new wavelength, of the new amplitude, sorry, of the new amplitude? So what is the value of our new amplitude going to be now? So they said that it's doubled, and we want to know what is the value of our new amplitude in meters. I'll give you guys. Okay, where do you, I see someone is lost. Where do you feel like you're lost? Oh yes, Kacheho. 2.4.2. Okay, so we were asked for the wavelength of this wave, right? And we had found the frequency. So do you understand the frequency part? Okay, perfect. Now, on our formula sheet, you'll get this formula here. So either on your formula sheet or your teacher, whichever, whatever they test you with, they're going to give you this formula that says speed is equals to frequency times wavelength. Right. Now we said we could either write it like this and then use algebra to kind of move some stuff around, or we can draw our triangle and say that this is our speed, this is our frequency, and this is our wavelength, right? We are looking for wavelength, right? So we are going to cross out our wavelength, and we're going to say what is left. We're left with speed over our frequency. Oh, sorry, this is 2,5. Speed over our frequency. So then we had V over F, which is essentially what we had here, except here I was doing it algebraically, but I can do it the other way around. So we would have, ooh, just moves everything. Okay, so we can write it as wavelength is equals to the speed over the frequency, right? And so we said our speed, we were given that our speed is 12 meters per second, right? So we then wrote, write 12 over the frequency, which we found to be 2.5. So then 2,5. And then if you put this in your calculator, we should get 4,8 meters. Did you get 4,8 meters? Okay. Does that clear things up? Are you good now? Okay, perfect. Okay, I see some people have put the amplitude in the chat, just perfect. You guys are getting 0.2 meters. Okay, that's perfect because we told that our displacement here is in centimeters, and so that times 2 would just give 20 centimeters, which is going to be 0.2 meters. Okay, perfect. Now let's see what the next question says. Okay, now this one, again, we're still on waves. We're told that in the diagram, there are two pulses, P and Q, and they move towards each other in a slinky coil. The pulse P has an amplitude of 12 centimeters, and the pulse Q has an amplitude of 8 centimeters. The pulses meet at position Y, which is, and let's assume there's no energy loss, right? Okay, so what is the term transverse wave? And we looked at this in our slides. It's a single disturbance that occurs in a medium where the particles of the medium move perpendicular to the direction of propagation. So if we had our wave looking like this, our particles are moving up and down, but our wave is actually moving left to right. So that is how we would do that. Okay, so that's how we would describe it, but that's just a definition. So you can go and memorize that so that you can have some free marks. Okay, then they say, write down the phenomenon that occurs when two pulses meet at position Y. So we spoke about this in the slides. What is that? What is that phenomenon called? Where they meet together at Y. Yes, the principle of superposition, right? So they superimpose on each other, right? So so here they try to trick you a little bit. You might have thought this is a transverse, this is a longitudinal wave because it's a slinky, and that's how we usually see longitudinal waves. But this person is moving this thing up and down, so they're making a transverse wave with a slinky. So you'll actually just get, this is a wave here and another wave here. So that's a transverse wave. Okay, transverse pulses. Okay, calculate the amplitude resulting when P and Q meet at position Y. So what do you guys think that amplitude is going to be? When they meet at position Y, we're told that P is 12 centimeters and Q is 8 centimeters. So this is either constructive or destructive. So there's two different things that we do in both of those cases. So what is that amplitude? Okay, perfect. Yes. So because they are on the opposite sides of the reference point, we will say that they are destructively interfering with each other. And so we'll have 3.3. So we'll have, we're saying the amplitude, the positive amplitude is the 12 one. So we'll have 12 plus minus 8. So this will just be 12 minus 8, which is going to give us 4 centimeters. Perfect. Okay, so that will be the amplitude at y. And then 3.4, pulse P travels a distance of 0.6 meters in 5 seconds. Calculate the speed of the pulse. Okay, so the pulse travels at a distance of 0.6 meters in 1.5 seconds. What is the speed of the pulse? So this is very elementary physics question. So you couldn't really use a formula, but you're using a similar principle. So this is just, they've given you a distance, they've given you a time. What is the speed of the pulse? Okay, perfect. We have an answer. So this is just speed is distance over time. So we know that our distance is 0.6 meters over our 1.5 seconds. So our speed is going to end up being 0.4 meters per second, or 0.4 meters per second, like that. Okay, perfect. Well done, guys. Okay, then they say, let's see. Okay, then we have this one. So we have a tuning fork with a frequency of 100 hertz, and it creates a sound wave illustrated in the sketch below. What type of wave does this tuning fork create? Is this a longitudinal wave, a transverse wave, or is it an electromagnetic wave? So this is a longitudinal wave, right? Because you see like parts that are close together. So a sound wave is usually made from pressure. So the way that we hear sound is that vibrations come from whatever is making the sound, and then it causes our eardrum or our eardrums to like move and flop around, and that's how it interprets sound. And so this is how sound waves propagate. They just like vibrate, that cause these vibrations that cause these long parts, or parts where the sound waves are far away from each other, and parts where they are close to each other. So R, like we said, R is where the molecules are tightly tied together, and this is called compression. Compression. So we're answering this one. And S is known as rarefaction. Rarefaction. Okay. So now they told us, what did they tell us in the question? They said a tuning fork with a frequency of 100 hertz has created a sound illustrated and sketched below. Calculate the period of the sound wave. So the period of the sound wave produced by the fork. Now, this isn't, oh, it is on our formula sheet. So let's find the period of the sound wave. So we've got some answers coming in. I'll give you 20 more seconds. What is the period of the sound wave? Okay, so like we said before, the symbol that we use for period is T, and in our formula sheet, we're told that T will be 1 over the frequency, which is going to be 1 over the frequency, which they give us is 100 hertz. And so that our period is going to end up being 0.01 seconds. Perfect. Okay, cool. Well done, guys. Okay. Does anyone have any questions so far? Anyone confused? Anyone deeply worried? No questions? If you do, just pop them in the chat and then we'll answer them as they come. Okay. Now, this one is kind of a theory one, and it shouldn't be that long of an explanation. But during a thunderstorm, it is noted that the flash of lightning is seen before a loud roar of thunder is heard. What would the explanation for this be? I'm going to tell you, just think about it. What do you think? Why do we see lightning first, and then after a while, you can then see you can hear the thunder after a while? Okay, this is because light travels faster than sound. Right, perfect. Well done. Light, the speed of light is faster than the speed of sound, and so we can see the thunderstorm. We see it a lot quicker than we hear it. I'm not sure how true this is, but my mom would always say, if you count the flashes, so you count the seconds after you see the flash, you can tell how far the lightning strike happened. So like you'd see the flash, and then you count 1, 2, 3, I'm not sure how true it is, and then you hear the sound, then you'd say, okay, it's 3 kilometers away. That's where the lightning happened. But yeah, that's perfect. Okay, cool. Now we have electrostatics, which is also nice. So here I have 2 metal spheres. First of all, let's look at these charges. I have one that has a negative 6 times 10 to the power of minus 9 coulombs. And I have one that has a positive 2 times 10 to the power of minus 9 coulombs. And so we said when we have something that has a negative charge, it means that it has an excess of, oh no, I'm giving away. No, sorry. So 5.1 says, how does the number of electrons on sphere B compare to the number of protons? The number of electrons on sphere B compared to the number of protons on sphere B. Oh yeah. So how's the number of electrons versus the number of protons on sphere B? So you can see sphere B has a positive charge. So it's going to have an excess of electrons, it's an excess of protons. So it's got a loss of electrons. So the number of electrons is going to be more than the number of protons. Okay. Oh no, sorry. Number of electrons is going to be less than the number of protons. Sorry. Less than the number of protons. Okay. Okay, cool. And then to give a reason for your answer, we know that sphere B is positively charged, and so it has excess electrons because it has lost electrons. Okay, or had them stored. We don't know. Okay, then we have the principle of conservation of charge, and that's just a definition. So you must always remember to do your definitions because they keep popping up. I don't think you can ever escape definitions.
It's like escaping the grandma from feeding you. But yeah, the conservation of charge is the net charge of an isolated system. The conservation of charge states that the net charge of an isolated system remains constant during any physical process. Okay, perfect. So now it says, in which directions are the electrons flowing while sphere B and sphere C are in contact? So what happens is these spheres are allowed to touch, and after they touch, they're separated to their original position. So they start here, they are allowed to touch for a brief moment, and then they're separated to this distance once again. Doesn't matter what the distance is. But then they say, in what directions will the electrons flow while spheres B and C are in contact? Let's see. Okay, so these were the charges. I'll write them down here. So this had a -6 times 10 to the, oh, did I forget something? Yeah, -6 times 10 to the power of -9. And then this one had a charge of +2 times 10 to the -9 coulombs and coulombs. So which way would the electrons be flowing? Are they going from C to B or B to C? Okay, they'll be moving from C to B because we said electrons travel from negative to positive. Thank you guys, that's perfect. Okay, cool. So we'll know that they're moving from C to B. And then they say explain what happens there. So the sphere C has a negative charge and thus has an excess of electrons which are shared equally, and only the electrons flow from C to B. Okay, so that would be your explanation. Then they say calculate the charge on each sphere after they are separated. Okay, so we have a formula for this. What is the charge on each sphere after it is separated? So I'll give you guys 2 minutes for this one. You should be able to do it in 2 minutes. Oh, let's see. Did I put? No, I don't think you can use this one. Hold on. Did I put my? I was supposed to give you guys the equations. Well, the 2 equations that you get on your formula sheet are going to be Q is equals to Q1 plus Q2 over 2, and the other one is going to be N is equals to the change in Q over QE. So we're looking for the charge after they're separated. This one starts at -6 times 10 to the power of -9 coulombs, and then it is +2 times 10 to the power of -9 coulombs. Okay, so to calculate this, we're going to use this formula over here, which says that Q is equals to Q1. So Q1 would be, we can choose whichever one we want. We're going to say this is +2 times 10 to the power of -9. And then we're to add Q2, but that Q2 is a negative, so it's just going to be -6 times 10 to the power of -9 over 2. And that should give you minus 2 times 10 to the power of minus 9 coulombs. Oh, that might have been difficult to write in the chat. But yeah, this is what you would get. Shout if you didn't get this, but this is what you should be getting. Okay. Then the second question, or not question, but 5.2.5, it says calculate the number of electrons transferred between the spheres. Right, now we said we used this formula over here, and it says the number of electrons is equal to the change in the charge over the number of the charge of an electron. Sometimes they write it as QE, sometimes they write it as E. In your constant sheet, it's written as E, right? So here, you would do the same thing that you did for Q for the change in electrons, except now you're going to minus them. So you're going to say Q1 minus Q2 over E, right? So here we'll have, let me just zoom out a little bit. So here our Q1 is, oh sorry, Q final minus Q initial. Ooh. Let me just erase it. So we said the electrons come from the C, from C to D. So that's the one that's giving away all its electrons. So we look at its Q final. So what is its charge at the end minus the charge it initially had, right? So the charge that it has at the end is minus 2 times 10 to the power of minus 9, which both of them have, right? And we're going to minus the initial one, which was minus 6 times 10 to the power of minus 9, all over the charge of an electron, which we have here, right, as minus 1.6 times 10 to the power of minus 19. Okay. And when you put this in your calculator, you should get 2,5 times 10 to the power of 10 electrons. So that's how many electrons moved from sphere C to sphere B. And so we used the fact that they were coming from the sphere C because that was the negative one and moving to B. And so we looked at what was the final value for the charge on QC minus what it was initially to find the change in the charge, and then we divided that by the electrons. Okay. Okay, I hope that makes sense for everyone. And then this one is just a theory question. It says, what type of electromagnetic wave is used in Wi-Fi? And that is radio waves. Radio waves. Okay. Then they say, state one advantage that the type of radiation named in 6.1.1 has for the use of Wi-Fi. So radio waves have a long wavelength. And so they can be transmitted over longer distances. But this would have been in your notes. So this is just like a theory question that you would have had to practice or remember. Okay. Then the last question for electromagnetic waves is, or for waves, is I have a photon. So remember, the photons are little packets of light, and they are associated with a certain electromagnetic waves that has 1.46 times 10 to the 24 joules of energy. All right. And then they say, define the term photon. Now we said photon is a particle of light energy. So that's as basic as you need to make it, or you can give a longer explanation. Then they say, what is the speed at which this electromagnetic wave travels? Right. Now we said the speed for all electromagnetic waves is going to be 3 times 10 to the 8 meters per second. This one is a free one because it's going to be on your formula sheet. So all you need to do is read off your formula sheet if they ask you that. That's a free mark. You just need to remember that that's the speed of electromagnetic waves. Okay. Then they say, calculate the wavelength of this electromagnetic wave. So this is 3 times 10 to the power of 3 times 10 to the power of 8 meters per second. Then they say calculate the wavelength. So I want you guys to tell me, what is the wavelength of this electromagnetic wave in meters? So we have the energy, we have the speed that it travels at. I want the wavelength of this particle. What is the wavelength going to be? Remember, we have a specific formula for our electromagnetic waves. So it's not going to be the same as C is equals to the frequency times the wavelength. We have a specific one for photons. What is the wavelength for this electromagnetic wave? So before we used our speed, our wave speed, which was V is equals to frequency times wavelength. Here we're going to use the other one, which is, so 6.2.3, it is going to be E is equals to the Planck's constant multiplied by the speed over the wavelength. Now, to get this wavelength, you can move some stuff around, right? So multiply both sides by the wavelength and then divide both sides by the energy. But eventually you just have wavelength is equals to Planck's constant multiplied by speed over the energy, right? And so that should give you Planck's constant. They give it to you as 6,63 times 10 to the power of minus 34 multiplied by the speed of light, which is going to be times 3 times 10 to the power of 8. And this is all going to be over E, which is our energy, which they gave us as 1,46 times 10 to the minus 24 joules. And so you should get your wavelength as 0,136 meters. Or if you're doing it to 2 decimal places, you should get 0,14 meters. Okay. Okay, then it says, if the wavelength of this electromagnetic wave is doubled, what is the effect on its penetrating ability? So its penetrating ability is basically its energy. So if we have our formula, which says E is equals to hc over the wavelength, right? If the wavelength is doubled, right? So normally in fractions, if I have 1 over 100, if I have 1 over 100, that's going to be smaller than 1 over 10, right? Because the bigger the denominator is, the smaller the whole fraction is going to be. So if I increase the wavelength, that means my energy is going to decrease. Right. Okay. And then the reasoning for this is just wavelength is inversely proportional to the energy or the penetrating ability. Perfect. Well done. It does decrease. Okay, cool. And then the final section, my favorite section. Okay, we're going to try and zoom through this one. We have a circuit. Is this a parallel or series circuit? Series. I don't know. If we have our current going this way, and then this way, and then this way, and then this way, and then, oh, it meets this junction over there, it can go down here, there, or there, right? That means it's a parallel circuit. Perfect. Okay, cool. So define the term voltage. We said voltage is the work done in moving a unit of charge. Then they say calculate the voltage of all three cells. Okay, so they've given us joules of energy and charge, and they want to find the voltage. So what is the voltage, not of individual cells, but of all the cells together? So what would the reading on this voltmeter be? So they've given you joules, they've given you charge, and they're asking for voltage. Joules, sometimes, I don't know, some people like to call it work, but I don't know. I think it is, maybe not. Okay, so we're looking for voltage in the given joules and charge. Perfect. So we'll have voltage is equals to work over charge, which is going to be 90 over 20, which is going to be 4,5 volts. Perfecto. Okay. Then they say, what will the potential difference of each cell be? Now this one's nice and easy. We just want to know what is the voltage for one cell, but it depends here on how many cells we have. Do we have one cell, 2 cells, 3 cells, 4 cells, 5 cells? I don't know. 7.1.2 or 3. 3? 3. So what is the voltage of one cell? Or what is the potential difference, sorry, of one cell? 0.75, perfect. So our potential difference is just going to be 4.5 divided by 3 because we have 3 cells. So this is going to be 0.75 volts. Oh, sorry, not 0.75. We're looking for potential difference. It's going to be 4.5 is 1.5, perfect. And to look for 1.5 volts, perfect. Okay, cool. And then our last question. I'm gonna miss you guys. It says a charge passes through. Is it actually? No, it's not the last one, but the last one is a theory question. It says a charge of 30 coulombs passes through a point in the main circuit in 40 seconds. Determine the ammeter reading in the circuit. So they've given us charge and they've given us time, and they want us to find the ammeter reading, which is the current. So 7.2.1, what is our current going to be, or what is the ammeter reading going to be? Maybe Cindy was going faster than all of us. because she has the answer for this one. Oh, yes. Oh, okay. So here we were just looking for current, and we're told we know that current from our formula sheet is equal to charge over time, which is going to be charge, which is 30 coulombs, over the time, which is 40 seconds. And so our current is going to be 0.75 amps. Woohoo. Okay. And then this one, 7.2.2, what is the effective resistance in the parallel combination of the circuit? So let me just bring this, I don't know if I can. I can bring it back down here. So this is our circuit, right? I want to know, it's gonna go normal now. I want to know what is the, oh my gosh. Can I put it down here? Yeah. Okay. I want to know what is the resistance of the circuit, or the effective resistance. They haven't told us anything in this diagram. They haven't told us what we know what the voltage is and we know what the current is now, but they haven't told us what this resistance plus this resistance plus this resistance. We don't know what any of the resistances are. So how can we find out the resistance of the circuit? Okay, so we have a 60 ohm or 6 ohm. Cindy was saying 6 ohm. Okay, which is correct. And she got that using the V is equals to I times R, or R is equals to V over I, right? Over I. We know our voltage. We calculated it before to be 4.5 volts. And we know that our current is 0.7. So from here, we can just get our 6 ohms. Okay. And then the last question is just, if one of the light bulbs burns out, so if this goes out, how would the brightness of the other two bulbs be affected? Would they be brighter, dimmer, or would they be no change? They would be dimmer. The effective resistance will increase, but the total current will remain the same. So that will result in our bulbs glowing dimmer. Okay, well done, guys. That was so good. Give yourselves a round of applause. Okay, cool. If you're able to do all of those, then you should be comfortable for your test, barring any other hindrances. Tomorrow's session has chemistry, so we'll be going through chemistry papers. If you're really struggling with chemistry, you can come back tomorrow and see some chemistry. I'm going to stay on for the next 10 minutes just in case somebody has any questions. But yeah, if you guys are done, then you can just log off, and I'll see you next time.